I'll be talking here about a search for high supersaturation, and in particular during Guamazon's rainy season. And the reason I and others are so interested in high supersaturation is because of the role it plays in this really interesting hypothesis of warm phase invigoration, which, for context, works like this. It's the idea that if we have more aerosol in the air, then that would lead to more cloud droplets in moist convection. And all else equal, that would tend to lower the supersaturation in the cloud, which means that there'd be more latent heat that would have been released by that point, which will lead to a higher buoyancy and a faster updraft speed. So one of the linchpins to this chain of logic is the existence of supersaturation in the air to begin with. If there is no supersaturation in the unpolluted clouds, then when you add aerosol, you can't lower non-existent supersaturation. And in fact, you need not just some finite supersaturation, but you need a supersaturation that's on the scale of about 10% if you want to get a significant invigoration result. So fortunately, we can go and look for this high supersaturation. Supersaturation is just RH minus 1. And if we're looking at a cloud parcel in a Lagrangian sense, following along with it, and its relative humidity or supersaturation is constant in time, then we call that quasi-steady. And in that case, we can write down an equation that would give us the supersaturation. So S, the supersaturation would be equal to F. It was just a thermodynamic constant, takes a value of about 2.5 seconds per meters cubed, and then times the vertical velocity divided by the number concentration of the droplets and the mean droplet diameter d bar here. And fortunately, all three of these things on the right-hand side are observable in situ with an aircraft. And so a handful of studies have gone and looked and calculated supersaturation with aircraft. And in fact, 2 years ago at the ACPC meeting, I presented one such study where we calculated supersaturation during the Go Amazon dry season using instruments aboard the Halo aircraft. And in that presentation 2 years ago, I showed the results of the calculated supersaturation in those cloudy updrafts. What you see here is a log axis for supersaturation down here on the x-axis, and just the density on that log axis of the observations on the y. And which one here's the distribution, which has a median of about 0.1% for supersaturation. As I mentioned, you need about 10% supersaturation to get a substantial warm phase invigoration effect, which I've colored in as gray here. And so obviously the red distribution is far from the gray distribution in this dry season case. Now, 2 years ago, when I presented this result, I had a slide about a caveat, which I will replicate here. So 2 years ago, I said, well, hey, there's a caveat. And that is that we used measurements from the dry season. And the reason that's a potential problem is that in the dry season, you don't have as much moist convection and rain scavenging aerosols from the air, cleaning the air out. And so you tend to have a more polluted atmosphere. And so if we're measuring the supersaturation in clouds in these more polluted conditions, we're not really measuring the supersaturation directly in the unpolluted conditions that you might expect aerosols would then reduce as part of the invigoration mechanism. Now I presented a counter caveat to that, which is that we could take the results we had from the dry season and extrapolate them to the wet season with a scaling that we put together. It's a very simple scaling where supersaturation would go like the aerosol concentration to the minus 2/3 power. And if we apply that scaling, we argued you would still not get a supersaturation on the order of 10%. So if we look back at this distribution of supersaturation values from the dry season, and then we use that scaling would predict that the rainy season should sit right around here at about 0.5%, if we use that scaling. So what I'm going to do here in this talk is try to overcome this caveat and just go to the rainy season directly. and take measurements. So 2 years ago, we used Halo. For this study, I'm using the G1 and its transits through moist convection during the rainy season. And to give you an example of what that looks like, here's one such transit. So the photo here is from the forward-facing camera on the G1, and this is the photo about 10 seconds before it transits the cloud. And then overlaid is shown a time series of vertical velocity in black, and it's a 2-minute time series centered on the transit. So you'll see that the vertical velocity of the wind got up to about 6 meters per second. So this is a semi-moderately interesting convective updraft. And the little yellow X just denotes the time the photo's taken. And then we've got these red dots on here. And the red dots are the supersaturation that are calculated using that quasi-steady equation, calculated at the times where we think the quasi-steady approximation is valid. And you'll see that the values are around 0.5% here. And so I've put in 2 pink lines as just visual references. The lower one is 0, and the upper one is 1%. And so the red dots for supersaturation sit between 0 and 1% in this case. Now let's zoom this guy out. I'll just put it there. And let's add in all of the transits that had measurements of supersaturation in them, where we think they were quasi-steady measurements. And here they are. The top row, the forward-facing camera wasn't working, so that's why there's no photo there. But otherwise, these are all basically the same types of thing. And if you scan across this with your eyes, you'll see that the red dots are all sitting between the 2 pink lines, which means that the supersaturation is between 0 and 1% for all of these cases. So if we want to be slightly more quantitative and make a distribution, we can go back to the result that I shared 2 years ago, and we can add on to this the distribution of supersaturation from the rainy season as measured by the G1. And what we get is this blue distribution. Just toggling back and forth here a little bit. And the prediction was pretty good here. We have in this distribution a median supersaturation of 0.5%, as you would have predicted from the scaling relation. So again, it's still sitting far from the gray area where you'd expect to get substantial warm phase invigoration. And this is, in a way more interesting than the dry result, because this was measured in the time over the Go Amazon where it's been suggested that the warm phase invigoration mechanism is operating. Okay, I want to make just one other comment about calculating the supersaturation values and how important it is to be careful about applying this quasi-steady approximation to get supersaturation. So this is a bit of an aside, but I think it's an important one. So this is that same blue distribution. It changed to green. That's really bad presentation tactic there. I apologize. It's the same distribution. And I've listed here the criteria that I required cloudy parcels to meet if they were going to be interpreted as being quasi-steady, such that we could calculate the supersaturation. So it's that the condensate mass fraction be greater than 10 to the minus 5, which is a really low threshold. W, vertical velocity, greater than 2 meters per second. Height above 1 kilometer to avoid some of the stuff happening at cloud base. We're more interested in the updrafts in the free troposphere. And then this last one, W greater than 2 times the largest magnitude of vertical velocity in the clear air, is probably the more interesting one. And the rationale for this is that, well, if we're looking in the clear air and we see upward motion, we know that's not quasi-steady in the free troposphere, because the free troposphere is stably stratified, and so I cannot have steady clear air ascent in the free troposphere. And so if I see motion in the clear air that's rising at some speed, and then I see a comparable speed inside the cloud, it really raises the question of whether or not that speed inside the cloud, that eddy rising inside the cloud, is also just a transient eddy like we see outside. And so demanding that the vertical velocity kind of sit above and beyond the distribution of vertical velocities we see in the clear air is asking that that cloud updraft kind of sit apart from the turbulent motions we see in clear air, and therefore is more likely to be steady. I'm not claiming that these are, the exact conditions one should use to identify quasi-steady air, but these are the conditions I proposed in this most recent paper. So what happens if you don't do these? If you don't do these, it's very easy, or do something like this. It's very easy to get spuriously high supersaturation values. So, imagine we throw away a bunch of these conditions and we just require that the condensate mass fraction be greater than 10 to the minus 5, and we require that the air be ascending. Well, okay, we can do that, but now we're going to get a bunch of really small values on this wing over here, and we're going to get some larger values on this tail over here. And a lot of these are kind of more obviously not real values. It's pretty easy to get a high supersaturation if you've got slowly rising air with a single large drop in it. You just infer that if that's rising in a way where RH is constant, you must have a really high supersaturation, when in reality it's probably just a transient eddy. If you go even further and say, hey, let's not even have a finite threshold on cloud condensate fraction, then you get something like this, where we're, you know, saying that we see supersaturations of 100%, 1,000%, even 10,000%. Now, this is obviously wrong, and so no one would go and try to publish these numbers and say they've found ginormous supersaturation. But more insidious are these ones that are kind of in between. There's a collection of values where we're not really sure if these are quasi-steady. And I think that's where we have to be really careful about applying the quasi-steady approximation where it's most likely to be valid. Okay. Um, so, so I've presented these results showing that, over the Amazon, from the measurements we have, we don't see supersaturation really anywhere close to what's needed for warm phase invigoration. But that doesn't mean it doesn't exist somewhere, sometime, some type of convection, right? And so it's still a really interesting question from my perspective of whether you could find results somewhere on Earth, sometime, a type of convection that sit here on this axis. I think it's a really interesting, outstanding question. And this is the last slide I have here. It's the last slide I concluded on 2 years ago at the ACPC meeting, which is stating my opinion that we should have a campaign that's focused on convective supersaturation. This would be a campaign where we focus on a place and time with low aerosol concentrations, where we're ideally penetrating mature convective clouds and doing what these types of planes are good at doing, which is measuring vertical velocity and the size distribution of cloud droplets. And that's where I'll wrap up.